So in our previous video, we looked at wave motion. So here in this video, we're going to look at the 5 major properties of waves. Okay, so the 5 major properties of waves are amplitude, wavelength, frequency, period of a wave, and the speed. Okay, so we have a diagram here. Okay, so what we mean by the maximum displacement of a wave from a point, okay, away from its undisturbed position. So remember last time we looked at something like this. Okay, so what we have here, this line here, okay, that's what we call the rest position. Okay, so a number of particles are in this rest position. Okay, so you have particles in this rest position. We can show them like this. Okay, so let's say these are the particles in their rest position. So as we discussed earlier on in the previous video, I said once we introduce a disturbance there, okay, we give a disturbance. Okay, once we give a disturbance from there, the particles here will begin to vibrate. Okay, and once the particles start vibrating, it depends on the type of vibration. Okay, it could be an up and down vibration, which will give a transverse type of a wave, or it could be a to and fro or back and forth vibration that will give a longitudinal type of what wave. Okay, so this we call it the rest position. So depending on how these particles will vibrate, okay, in this medium, okay, so depending on how the particle will vibrate, okay, so now the maximum displacement, okay, so as we can see there on the diagram there, find that you have a wave shown like that. Okay, so now what's going on here is that these waves here, they get displaced. Okay, they start moving like that, okay, from their rest position. Okay, so as they're being displaced here, we're simply looking at the maximum displacement. So the maximum displacement will be at this point there. Okay, similarly again, the maximum displacement will be at that point there. Okay, so the maximum displacement, we simply need to measure, okay, the height, okay, or the length from there to there, and this will give us our amplitude. Okay, so as the particles are being displaced, okay, from their rest position, the maximum they can be displaced. Okay, so that's the amplitude. Also here, that is the what, the amplitude. Okay, so the amplitude, so here the rest position here, the 0 mark. Okay, so you have positive numbers going this side and negative numbers going this side. Okay, so if here you can have a 2, okay, you can have negative what, 2. Okay, so the displacement here from here to there, it's 2, from there to there it's negative 2, since you're going down the axis, okay, down the y-axis. Okay, so from our diagram there, we can see what is circled there as the amplitude. Okay, what has been labeled in green by the arrow, that is simply the amplitude. Okay, so particles are undisturbed before there is a disturbance or vibration. Okay, then they begin to vibrate. Okay, here is another a diagram also showing how, so you can see the particle there as it's moving. Okay, it reaches the highest point. Okay, so the distance from that highest point to the rest position, that equals the what, the wavelength. Okay, so that's pretty much all we can say about the amplitude. Okay, so we'll go over to the next property, which is the wavelength. Okay, the wavelength again. So back to our video again, back to our the same picture we had here. We can see that we have a wavelength labeled there. Okay, now a wavelength, would define it in so many ways. Okay, we define a wave length in so many ways. Okay, so from here, so what we should know first of all is that this highest point here, okay, we call this hill, it's called a crest. Okay, it's called a crest. Then the downhill here, these we call them troughs. Okay, we call these troughs. Okay, so now in a case now where you have something like this, okay, you have a number of crests and troughs. Okay, a diagram like this. So we have a number of crests and what? Troughs. Okay, so this is a crest, a trough. Okay, so I have a crest and a trough. So similarly here we're going to have a crest and a trough, the crest there. Okay, so the minimum distance, okay, the distance between two successive crests, that's the definition number one for your wavelength. So this distance from there to there, okay, so wavelength is simply, from the first definition we're going to have, we're going to say it is the minimum okay, or the distance between two successive crests, okay, it's represented by the symbol lambda. Okay, so definition number one, wavelength is the distance between two successive crests. Okay, definition number two, wavelength is the distance between two successive troughs. Okay, so from this trough to that other trough, that is also the wavelength. Okay, so as we can see there, you have particles moving. Okay, so from one crest to another, it's giving us wavelength. From one crest to the next crest, it's simply the wavelength. Okay, so we have two definitions of from a distance from one crest to the next crest, one trough to the next trough. Okay, another definition of wavelength is simply the distance it takes to form one complete wave. Okay, so one complete wave. Okay, the distance it takes to form one complete wave. Okay, so one complete wave, okay, just to make it simple here, one complete wave is simply what? Okay, one complete wave. What is one complete wave? So one complete wave is simply one crest, okay, one crest and one trough. Okay, one crest and one trough. Okay, so one crest and one trough, this makes a complete wave. Okay, so this is one complete wave. Okay, one crest, one trough. Right, so this is one complete wave. Okay, one complete wave. So the distance it takes to form one complete wave, okay, the distance to form one complete wave, that is wavelength. Okay, so in other words, what we simply mean is the distance from here to here, this distance is also the wavelength. Okay, so what? The wavelength. Okay, so here in this diagram you can see we call this a circle. Okay, we say one cycle. So one cycle, one wave, cycle, one wave. Okay, so one cycle gives us the wavelength. Okay, so this from here to here is a cycle, so the distance you measure here to be wavelength. Again, from here to here, that's another cycle, the distance you measure here, it's wavelength. Okay, so we have three definitions so far: the distance from one crest to the next crest, okay, the distance between two successive crests, okay, so this crest and this crest, okay, the distance between two successive crests, the distance between two troughs, okay, that all define wavelength. Okay, then apart from that, we've said the distance it takes to form one complete wave. or the distance it takes to form one complete cycle. Okay, this is one complete cycle. Okay, all that is what? Wavelength. Okay, then apart from that, the wavelength can also be defined as the distance, the minimum distance at which a wave repeats itself. Okay, so as you can see, these are oscillations. Okay, they are oscillations, they're simply repetitive patterns. Okay, so when you have one crest and one trough, also here you have one crest and one trough, so these are just repetitions. Okay, as we can see here, as the wavelength there, you have this wave and the particles moving like that, so it's just a repetition. Okay, it's a pattern. Okay, so from here we can say the wavelength is simply the minimum distance at which a wave repeats itself. So once a wave is formed here, this will be a repetition. Okay, crest and trough, so crest and trough, crest and trough, all that is simply a repetition. Okay, all that is simply a repetition. Okay, so that's what we can say about a wavelength. Okay, the other thing about a wavelength, let's look at this figure here on a longitudinal wave. Okay, so according to that diagram here, the simple representative, okay, we can represent it like this. Okay, so what we have here is simple illustration of a longitudinal wave. Okay, a longitudinal wave. Okay, so these will represent areas of where particles are closely packed together, so we call these areas compression. Okay, and then so also this is a compression. Okay, now these other areas here where particles are further apart from each other. Okay, these areas we call them rarefactions. Okay, so this is a rarefaction. Okay, these are called rarefactions. Okay, they are called rarefactions. So again, we can define wavelength as the distance between two compressions or the distance between two successive rarefactions. Okay, so that's all, pretty much all about the wavelength. Okay, then the next property is the frequency. Okay, so frequency is defined as the number of waves formed per second. Okay, the number of waves formed per second. That's, I think, the simplest definition we can give. Okay, that's what frequency is. Okay, the number of waves formed per second. Okay, so if we were to show this mathematically, say frequency, okay, is simply the number of waves formed per second. Okay, so time it takes to form those waves. Okay, that is the frequency. Okay, so you count the number of waves. Okay, so how do we count the number of waves? Okay, how to count the number of waves? So to say you have a wave shown like that. So for us to count this number of waves, what we do, say one wave. Okay, we've learned so far one wave is made up of a crest and a trough. So one crest, one trough, one wave. One crest, one trough, wave number 2. One crest, one trough, wave number 3. So in this case here, we're going to say frequency is equal to number of waves. There are 3 waves. Okay, some will say 3 cycles. Okay, so number of cycles. Okay, number of cycles, so 3 cycles or 3 waves is the same thing. Okay, 3 cycles or 3 waves. Okay, over the time it takes. So if it took, let's say this was at 5 seconds, you divide over the 5 seconds, and there you get your frequency. Okay, so frequency is measured in hertz, HZ. Okay, hertz represented by HZ. So let's look at now this animation here, this picture here. So you can see that you have waves being formed there and the time that it takes to form those waves. Okay, so another definition, or another formula for frequency is simply equal to 1. Okay, frequency simply equals the inverse of period, okay, which is 1 over t. Okay, 1 over t. Okay, so the period, okay, we go to the period. The period is simply the time it takes to form one complete wave. Okay, so the time it takes to form one complete wave. So for now we know one complete wave. Okay, this is one complete wave. So the time it takes to make this wave, okay, the time it takes to form this wave, we call that the period. Okay, so the period. Okay, so one complete wave is one crest and one trough. Okay, so then how long did it take? Okay, how long did it take? So this is what the period. Okay, so the period can also be the time, okay, elapsed from one crest to the next crest. Okay, that from the diagram there we can see the period there labeled from a crest to a crest. Okay, that time there in seconds, that is the period. Okay, so it's measured in seconds. Then lastly we have the speed. So the speed, that's the formula there. Speed is equals to lambda multiplied by frequency. Lambda there represents the wavelength. Okay, so speed is the same definition, the distance. Okay, the distance. Okay, the distance of a wave divided by the time taken. Okay, the distance of a wave divided by the time taken. Okay, or we can alternatively say velocity is equals to frequency multiplied by the wavelength. Okay, so as you can see there, the diagram there, you're seeing the wavelength has been measured, which is 3 meters. Okay, and it's consistent. So from crest to crest 3 meters, from crest to crest 3 meters. Okay, and the time it takes to form those waves, so 2 waves are formed per second. So 2 waves per second, that's the frequency, and the 3 meters there, that's the wavelength. So multiplied the 3 meters per wave, okay, that's wavelength. So 3 multiplied by 2 waves per second, that's frequency. You get a speed of 6 meters per second.